Howdy, Lynn. Can you hear me?
Yeah.
Cool.
I can hear you fine. Laura, there was something. No, you got to let me share my screen. So you've got to change.
Just did.
Fix that part.
You should be good to go now.
Share sound. There it is. Laura was explaining to me what I had to do.
Call Stephanie.
There. That works, right?
Yeah, it looks great.
All right, now this is the one that's always a problem with the sound. This one here.
Hey, Chris.
Hey.
I was just about to log in.
Okay, well, I logged in and it said the host is waiting. And then it said underneath, if you're the host, please sign in. So I did. So at least for now, I am the host. But if you're going to be catching the questions and whatnot,
You can make her co-host. She can be co-host.
Okay, let me just do this right now.
Well, can you try to log in right now? Just
Yeah,
in general?
That's what I'm doing, yeah.
Wow.
Anyway,
Hanford, is that Hanford, Washington?
Could you hear that? Chris, this is the one I'm always worried about. Could you hear this?
Yeah. Very
okay.
well.
Okay. All right. Well, the rest of them should be fine then. The rest of them should be fine.
Oh, cool. You're muted, I think.
I was saying, hi, Lynn, I'm Stephanie.
Hi, Stephanie.
Nice to meet you. So
I'm going to try to, I don't like this. This isn't really the right size for a Zoom background, the thing that I'm showing from LIGO. So I'm going to try to fix that.
Righty.
So Chris, when I went into our Zoom account, I checked off the box that says something like host needs to admit people. So if you it looks like you logged in as the host.
Well, once Lynn feels comfortable.
Oh, you can also be the host,
So do you know how to do that?
You can share host, you as host can make her co-host.
But I'm not familiar enough to know how to do that.
Oh, I don't know. Juanita always does that part.
I wonder if I already am, because I'm showing the ability to share screen and I see.
Well, he did turn share screen on for me, so.
And do you have share screen too? Okay, then we should be golden.
Yeah.
Cool. And the waiting room is enabled, right? Yes.
It is, yes.
And so, Lynn, we're not going to let anybody in until like 5:59,
yeah,
right before.
Yeah, my other question was, did people get individualized links, or is it just the same link for everybody?
Individual links.
Oh, darn, because my horseshoer was not allowed to register, and I sent him my email, but that might not work for him.
No, it might even kick you off. So that would not be a good idea. You're not supposed to share your individual link.
It didn't say that. It just said don't make it public.
Okay.
Anyway.
Yeah, that's odd. I went in to check the latest signups, and it removed your event from our account, meaning they must an hour before cut off registration.
Yeah, well, that's probably when he was trying to do it, right?
Yeah,
because he wrote me, like an hour before, and he said it won't let me register.
It's still on rfo.simpletix.com, Chris, it's just not on our, on the back end of Simple
Oh,
Text. but
okay,
you-
good.
It's still showing up as, you know,
Excellent.
being able to register.
Great.
Anyway, he told me wasn't allowed to register. So then, you know, I didn't know what to do about it. I can text him back and tell him don't, it was individualized links, it won't work.
It might be a good idea just in case, and just have him go to, like I said, to
He
rfo.simpletext.com.
went to that and it didn't work. It wouldn't let him in.
I'm seeing it now. I don't,
Everybody has their own links, so don't use mine or it might screw everything up. But it said that maybe they reopened it so you could try to register at Simple Text again.
Well, I'm now on RFO Simple Text, and it is not showing up on my screen. Oh, there it is. It's on the second page. That's odd. Yeah, it's there. Yeah, just have them go to Simple Text. It's on the second page of list of activities. So we should all be good.
And it's on the second page of the list of the activities at Simple Text. Anyway, usually the speaker has like a different one and then you put it in webinar format so you don't get Zoom bombed.
Yeah, I'm not sure we are signed up for webinar capacity.
Oh, with your Zoom account,
Right.
you mean? There, that one's my preferred.
Yeah.
That's my preferred
We have to
background.
upgrade.
Because it's actually like the right kind of background.
RFO Zoom is the host now. It just popped up.
Chris, I just did that.
Okay.
I just, if that's okay with you, I just made
Sure.
me, okay.
Yeah, I'm kind of doing triple duty here. I've got a poker game starting at 7:15. And so
Oh,
I'm
well,
cooking and I've been cleaning and
Should be done by them.
oh yeah. But I'm in the middle of cooking up some homemade gumbo right now. So I've been cleaning.
Well, I'm still trying to recover from riding my horse in 95-degree weather, and I've been sitting in air-conditioned room ever since I got back, and I'm still hot.
You know, Lynn, every once
But
in a while,
the ride
you're
was over. The
cutting
ride
out.
was over at noon, and I'm still trying to recover.
Right.
So
You cut out every once in a while, Lynn. Is there any other Wi-Fi in the house you can turn off to increase your signal? Because your voice cuts out.
well, no, I can't. This, you
Okay.
know, country living. What can I
Gotcha.
say?
Lynn, a person just popped up. It says Lynn Cominsky entered the waiting room. Do you think that's the
That's
person?
probably my horseshoer.
Do you want me to admit him and just him or her and just see?
Well, is it going to work or not?
Well,
I guess we'll find out, right?
I mean, we still have 5 minutes. So if it for some reason logs you out, then we at least have time for you to get back in. So
Yeah.
let me just oh shoot. Yeah, let me just admit that person.
See what happens. I mean, I can be on twice, right? So, but you should keep that second one muted and, you know, like you're going to do with all the other people, right?
Exactly. It actually automatically mutes people as they enter.
Okay.
So what, I'll give a brief welcome and then talk just briefly about RFO and then introduce you and give your bio that you sent us and then turn it over to you. Does that work for you?
Yeah, sure.
Okay.
Sounds pretty typical.
Yeah.
Well, we sure got a lot of folks from India signed up for this call, and from Hong Kong and Singapore.
Oh, it's like the middle of the night. Isn't it the middle of the night for them?
Probably.
Or the
Well,
like 6 in the morning or something?
Yeah, it might be
Crazy.
the morning.
Well, one person logged in at, shortly before 6
morning.
a.m. this morning. I think they
Oh
got
yeah, slight time zone problem. Anyways, Stephen, if that's really you masquerading as me, hi. You're muted and your name is coming through as me, but that's okay. We know you're not really me. Stephen and Barbara. anyway. At least they
they
got
can
it.
rename
So
themselves if they.
I'm sure he may not know how to do that.
Gotcha, Roger.
Yeah.
So do you do dressage?
No, I just do trail riding.
Oh, okay.
So we were out, it was a club ride, and they just had it on a Friday because of worrying that the parking lot would be too crowded on a weekend. And so we were at Jack London State Park, and we started at 10 a.m. and we rode in the shade for the most part. But when I got back to the trailer to, you know, put the horses in the trailer and take them home, it was like 95 degrees there.
Wow.
Yeah, it's hot.
Very hot.
Wow.
And then I got home and I've been sitting in the air conditioned room like since then until I took a shower, just trying to get myself to get my body temperature back down to normal.
Oh my goodness.
I've got my
It's
big
even
fan
hotter this
blowing
week.
on me right now.
Yeah. Well,
No
we
AC.
had the guys here fixing the air conditioning yesterday because we knew we were coming into this hot spell. Anyway, people, it's like 3 minutes too, so you might want to.
You want me to start admitting people?
Yeah, I could like share the screen and just put the, you know, put the title on, right?
Yeah, that's probably great.
Like that, right? Now you can
Yeah,
like
yeah.
start admitting people.
All righty.
And then maybe we can talk right at 6, or Stephanie, you can just get going right at 6,
Yes.
right after you admit people.
Yeah, I'm worried as LIGO keeps discovering more and more things, the talk is going to get longer.
Well, I'm really excited to hear it, and I bet everybody else is too. So I don't think many people will mind.
We are going to start in just a minute. I'm still admitting people are trickling in, so bear with me here. All right, I may need to pause to let more people in, but just want to welcome everybody to the Robert Ferguson Observatory Speaker Series. My name is Stephanie DeRomolar. I'm the volunteer coordinator for the Observatory, and we are very thrilled and honored to have Dr. Lynn Cominsky presenting for us today, and I will introduce her in a moment. But before we start, just wanted to remind everyone to please keep yourselves muted to minimize background noise. And we'll open up for questions at the end. You're also welcome to post questions in the chat, which I'll monitor and which I'll ask Dr. Cominsky to answer once she's done with her presentation. So just to tell, for those of you who are not familiar with the Robert Ferguson Observatory, the RFO is run by the Valley of the Moon Observatory Association, which is a 501(c) nonprofit comprised of volunteer, amateur, and professional astronomers. RFO has fulfilled its mission of offering educational programs about science and astronomy for students, the public, and in support of educators for about 25 years now. And it's still almost all volunteer run and typically serves about 9,000 visitors annually during a normal year. The observatory is located in Sugarloaf State Park here in Northern California and houses a 40-inch reflector telescope, the largest telescope in Northern California that's accessible to the public, a robotic 20-inch research grade or CCD telescope, and an 8-inch 2-meter long refractor telescope. The observatory has a robust volunteer program, and we have close to 200 volunteers who work tirelessly to deliver programs to the public, offer public star parties and solar viewing events, provide classes and workshops, and manage all the myriad of behind-the-scenes tasks to keep the observatory running smoothly. And as a little shameless plug for our volunteer program, it's a great way to get involved in the observatory. If that interests you, feel free to fill out a volunteer application on our website, rfo.org, and I can keep you informed of our next new volunteer training, next one actually coming up next month in August. We've kept these presentations in our speaker series free to the public to align with our mission of offering educational-based astronomy programs to our community. That being said, if anyone is so inspired to donate to the Robert Ferguson Observatory to ensure that we can continue fulfilling that mission, you can do so also through our website, rfo.org. So just briefly about Dr. Lynn Cominsky. She is a professor in the Physics and Astronomy Department at Sonoma State University, where she has been on the faculty for almost 35 years. She's an author of over 200 research papers and the principal or co-investigator on over $33 million of grants to SSU. Professor Cominsky is the founder and director of SSU's Education and Public Outreach Group, now renamed EdEon STEM Learning, which develops educational materials for NASA, NSF, and the U.S. Department of Education. In 1993, Professor Cominsky was named SSU's Outstanding Professor and the California Professor of the Year by the Council for the Advancement and Support of Education. In 2007, she was named a Fellow of the California Council on Science and Technology. In 2009, a Fellow of the American Physical Society, and in 2013, a Fellow of the American Association for the Advancement of Science. Recent awards include the 2016 Education Prize from the American Astronomical Society, the 2016 Wang Family Excellence Award from the California State University, and the 2017 Frank J. Malina Education Medal from the International Astronautical Federation. Sorry, admitting a few more people. In 2019, she was selected as one of the first 200 Legacy Fellows named by the American Astronomical Society. Her newest NASA project is NASA's Neurodiversity Network, which aims to develop resources and internships for teens on the autism spectrum. So without further ado, we again are so honored and pleased to have Dr. Cominsky with us today, and I will pass it over to her.
Thanks, Stephanie. Well, I wish that I could be at RFO right now, although it's probably rather warm, seeing everybody in person, because giving talks over Zoom is not really my favorite thing to do. So, because I cannot see all your smiling faces, and I will just have to wing it and hope that you're understanding me without me being able to get any real feedback from you all. So I'm going to tell you today about the discoveries made by LIGO and Virgo. I'm speaking on behalf of the LIGO and Virgo scientific collaborations. And the title of the talk, as you can see, is Space-Time Symphony, Gravitational Waves from Merging Compact Binaries. So let me just, there we go. This was the scene in February of 2016 at the National Press Club in Washington, D.C. And I was privilege to be there and to watch this all happen live and in person.
Ladies and gentlemen, we have detected gravitational waves. We did it.
Okay, so you can see everybody was really excited by the announcement. That's Dave Wrightsey speaking. He's the head of the LIGO Laboratory, which is based at Caltech and MIT. This woman is Dr. Franz Cordova, who was the director of the National Science Foundation at the time. This is Gabby Gonzalez, who was the LIGO spokesperson. And these two gentlemen are Ray Weiss and Kip Thorne, later to be two of the three Nobel laureates in 2017, when this discovery got the Nobel Prize in Physics. So why was everybody so excited? What are gravitational waves anyway? Well, if you ask any scientist, they will tell you they're ripples in the fabric of space-time. But that doesn't actually help very much to understand what gravitational waves are. That's just more astronomy jargon. It's important to know that gravitational waves were predicted by Einstein in 1915 as part of his general theory of relativity. And so one way to understand what's going on is if you look at this image on the left, bottom left, these are all little masses. And a gravitational wave is going through that region of space. And you can see what it's doing is it's squeezing and then stretching the space-time as it goes by. Now imagine you have lots of rows of those little masses, and you can see how it looks like a wave as it travels. Gravitational waves travel at the speed of light. That was another prediction from Einstein's theory of general relativity. And rather than being a wave traveling through a medium, they are actually deforming space-time as they travel, right? So they are changing the geometry of space. Now you may have seen a figure that looks like this at some point. This is how we usually explain the effects that masses have on space-time. And this is using Einstein's theory. So you have a big mass like the sun, and it deforms space-time a lot. And a little mass like the Earth deforms space-time just a little bit. But every time scientists show you this picture, it's really sort of a gross oversimplification, because it makes it look like there's this sheet of space-time and the masses only deform it in one direction. Now, really, space-time is a four-dimensional thing. There's 3 dimensions of space and 1 dimension of time. And these dimensions all get mixed up when things start to move and accelerate. And so really, it isn't just like a sheet underneath the sun. It's like all the space-time and all the dimensions around the sun are warped like that, or around any massive body. It's just that we can't draw that in 4 dimensions. And so we just draw the 1 dimension of warping and then put the masses in there so that people can sort of get a feeling for what it's doing. But it's really doing it in all 3 spatial dimensions, and it's warping time as well, which we really don't know how to draw. Now, Newton, on the other hand, you may have learned Newton's gravitational law. This is it right here, for those of you who've taken some beginning physics. In Newton's world, gravity was a force between 2 objects. It wasn't a warping of space-time. And the force between the 2 objects is transmitted instantaneously, and according to this equation. So it depends on Newton's big G, Newton's gravitational constant, the masses of the 2 objects, and the distance between them. And of course, there is that apocryphal story of Newton sitting under an apple tree and then looking at the moon, and then an apple falls down. And he realized that the same force that made the apple fall to the ground was keeping the moon in orbit around the Earth. And Newton's version of gravity, Newton's law of gravitation, it works great for pretty much any kind of experience that we humans have on a human scale. Where it doesn't work that well is when you get out into space and deal with really massive bodies or things that are moving really quickly and accelerating really quickly. So if you had to compare the two theories of gravity, Newton's theory versus Einstein's theory, in Newton's theory of gravity, space is flat and time is constant. In Einstein's theory of gravity, you have space-time and the four dimensions are all intertwined. If you move faster through space, you move slower through time, for example. In Newton's world, gravity is the force between masses, but in Einstein's world, gravity is the curvature of space-time. It can just be due to a single mass. You don't have to have a second mass. In Newton's world, gravity acts instantaneously, but in Einstein's world, gravitational information carried by gravitational waves goes at the speed of light. So it takes a finite amount of time for something to happen. If all of a sudden the sun disappeared, in Newton's world, the Earth would immediately notice the lack of gravity. In Einstein's world, it would take 8 1/3 minutes before that signal that the sun was gone got to us. The gravitational signal, and of course, the light from the sun would also disappear 8 1/3 minutes later. In Newton's world, light travels in a straight line. And in Einstein's world, light follows the shortest path through curved spacetime, which is usually called a geodesic. Okay, so now onto black holes. I'm sure that most people are familiar with the fact that black holes are infamous for not letting light escape once you get inside of a certain distance, which is called the event horizon. And the event horizon is defined by the region outside the black hole, that spherical shell at which the escape velocity is equal to the speed of light, which is, scientists always use the letter C for the speed of light. So if you cross the event horizon, you would have to be going faster than the speed of light in order to escape. That's not possible because the speed of light is the fastest speed, right? That's the cosmic speed limit. And when you go about forming a black hole, at least a normal sized black hole, we call them stellar mass black holes. They usually are formed when a star, a very large star, has a supernova explosion at the end of its life and the core collapses down. If it has more than 3 times the mass of our sun, it will collapse all the way down to a black hole. If it has less than that, it'll stop short and make a neutron star. Very dense nuclear matter. Usually neutron stars have about 1.4 to 2 times the mass of our sun. Now, the very first black hole that was discovered, and this was basically discovered at the beginning of the field of X-ray astronomy, and it's called Cygnus X1 because it was the first X-ray source discovered in the constellation Cygnus. It has a likely mass of about 16 times the mass of our sun, plus or minus 5. And the way they figured that out is by this radial velocity curve. This is a Doppler shift curve, looking at lines in this big star that the black hole that's inside this disk of matter is orbiting around. And so as the black hole and the big star, supergiant star, orbit around each other, they tug on each other, and the light from the visible light star gets Doppler shifted as the two objects are orbiting each other. And also there were a lot of X-rays coming from here, and you couldn't see anything else besides the supergiant star. But you could measure the mass of this by looking at this curve. And it turned out to be way larger than a neutron star because 16 solar masses is a lot bigger than 1.4 solar masses. And it's also much bigger than the 3 solar mass lower limit for black holes. And so other black holes that were found, and this Cygnus X1 was discovered in the late 1960s as an X-ray source with a rocket flight. And its counterpart was found in the early 1970s using data from the Uhuru satellite, which was the very first X-ray astronomy satellite. And so it got a good position, they could find the counterpart, the supergiant star, then they did the measurements, then they wrote the paper claiming that they had discovered the first black hole. So here's a little bit more history for you. These guys, this is Joe Taylor, this is Russell Hulsa. They got the Nobel Prize in 1993 for discovering a system of 2 neutron stars orbiting around each other. Each neutron star has a mass of about 1.4 times the mass of our sun, but one of them is a pulsar, so it's emitting very precise pulsations every 59 milliseconds. And you can use those pulses as a clock signal to track the orbit of these 2 neutron stars orbiting around each other. And what happens is the orbit is shrinking because of the emission of energy due to gravitational waves from this orbiting neutron star binary. And eventually those 2 neutron stars will coalesce and merge. And it was those mergers that LIGO was designed to detect, the merger of 2 neutron stars that have in orbit around each other. The orbit is decaying because it's losing energy, and someday it will, these things will merge with each other, but not any time that we're going to be able to see in our lifetime. Still, this famous plot shows the decay of the orbit, and the red points are the data points that they measured over now, more years than this, but this is sort of the classic figure. And the blue curve is the prediction from Einstein's theory of general relativity of how the system should decay, how the orbit should decay. And you can see it's like a perfect fit. As much as we try to prove Einstein wrong, he always is right with everything that we've measured so far. But this was not a detection of the waves themselves. This was actually indirect evidence that gravitational waves exist, because you could see the orbit shrinking, but you couldn't see the actual waves. So what if you could see 2 merging black holes using electromagnetic radiation, otherwise known as light? This is actually a supercomputer calculation using the full gravitational equations from general relativity. And interestingly enough, a lot of this numerical work was done in conjunction with Kip Thorne and in conjunction with that movie Interstellar, if anybody saw that movie that Kip Thorne advised on. So here you go. The 2 black holes are obviously these 2 black things. They're orbiting each other. But you see these little whiskers or like eyebrows. That's actually the image of the other black hole being warped around through space-time and showing up in a different place, right? It's sort of like lensed and warped. And then all of this stuff is due to the lensing and warping of space-time from the light from the other stars. Now you saw them merge, and then the whole thing sort of shook a little bit. Okay, so the Simulating Extreme Space-Time project, I'll show you that one again because it's really sort of pretty. They do these full supercomputer calculations to figure this all out. And it's really, very impressive that it takes hundreds and thousands of hours of supercomputer time to be able to do it. Okay, now they're just about to merge, getting closer. They're emitting gravitational waves this whole time, but this is the light waves. This video is showing you the light waves, and there it just sort of settles down and relaxes. Now here's what the same system would look like emitting gravitational waves. So you see they're going around. You see the waves going out through space-time. We drew the grid on there just so you can visualize it better. And now as they get closer, they go faster, the waves get taller, then they merge, and that's the end of the event. Just like one big blast of waves, and that's the end of the merger event. This one, is it going to start again? Do I have to back up? There you go. Okay. So you see how in the beginning, also the frequency of the waves is, fairly long. Wavelength is fairly long. Now notice how the peaks of the waves are getting closer and closer. The frequency is getting higher as the amplitude also increases. And then once they merge, that's pretty much the end of the action. Okay, so now let me tell you a little bit about LIGO. LIGO stands for Laser, Interferometer, Gravitational-wave, Observatory. And this is the cartoon version of how LIGO works. You have a laser beam that gets sent out through a beam splitter. The two beams go to the two ends of the interferometer, come back and combine at the beam splitter. Now we'll watch it a little more slowly. So this wave that goes to the mirror at the end turns around, gets reflected, comes back, joins with the other leg. If they totally destructively interfere, you won't see anything on the screen. So the null signal is the default until the wave comes through. And then it stretches and squeezes space-time, so the legs get a little bit different lengths. And then you get to see the waves interfering constructively, so you get a signal out on the detector. Okay, so as you change the length of the interferometer legs, the interferometer is in the shape of an L, you get, right, so here they are combining. Then you see how it gets brighter when it's constructively interfering. Now, obviously, this is grossly exaggerated because the amount of change in the length of the legs of the interferometer is very, very tiny. But if we scaled it correctly, you wouldn't be able to see anything in the video, so we have to exaggerate it. Okay, so here they're totally interfering with each other. You're not seeing the signal. When we have the wave come through and the length of the legs change, you get to see a signal. But obviously LIGO isn't this simple. So we did another video that shows what it looks like based on the CAD drawings and shows you the real path of the laser. So there's the control room in Hanford. And we're going to zoom in now. You're going to get to see a little bit of what LIGO really looks like. These legs are 4 kilometers long. These big things are called hams. They are help to do seismic isolation. Now we'll go inside one of the hams and we'll let the laser beam go out. And it bounces around off a lot of different things. So the first thing it's doing is called mode cleaning, and they're trying to sharpen up the laser beam to get a really exact frequency and also raise the power by sending it through these sets of mirrors repeatedly. So each one of these things is a horizontal amplitude modulation that does the seismic control. Here's the beam splitter. There's the 2 laser beams going off through the beam splitter. Now we'll go back out and look at what it really looks like. We'll zoom down this 4 kilometer arm to the end station. There it goes. Then there's a mirror there, and the beam bounces back and forth about 400 times before a photon can escape. So that builds up the power in each leg of the interferometer, so that you get a much stronger signal when you get to the mirror at the very end. Now, this is a 40 kilogram mass of glass suspended by millimeter thin optical fibers. Okay, now we're going to come back. We're going to focus back in on what happens when the beams come back together again in the beam splitter. Here they come. Now we go through some more mirrors, some more bounces, some more cavities that help you tune up the frequency of the light. And then finally, the output mode cleaner is where you get to read the signal. So just like in the other video now, we're going to let the wave come through and grossly exaggerate how much the legs change. And then you're going to see the signal that comes out from the changing length of the legs. So here is the signal. In fact, this is the signal that we saw. So it's a little bit of a fake, but this is the, pretty much the discovery signal. That's what it really looks like. Okay, so where are the LIGO observatories? There are 2 of them. The one that we modeled, they basically identical, but the one that we modeled is in Hanford, Washington. It's up in the nuclear where they had all the nuclear experiments, and it's a big nuclear reservation. And it's high desert, so you don't see a lot of trees. And the other LIGO that's identical is in Livingston, Louisiana, in the middle of the big forest where they're constantly cutting down trees. So the answer to the question, if you cut a tree down in the forest and no one's there to listen, would anybody hear it? LIGO hears it. They hear all the trees that got cut down in this forest, and it makes for a lot of background and a lot of noise during the daytime. So they tend to get better signals at night. And the two interferometer L's, the two legs, are oriented opposite each other. And if a light beam goes straight from one to the other, it would take 10 milliseconds to get there. So we can use the time delay between one observatory and the next to give us information about where the gravitational waves are coming from. So for example, if they were coming right from like this kind of direction, it would be equal, it would arrive equally at both of these, right? If it was coming from this direction, it would get to Hanford first and Livingston second. And so that tells you a big circle on the sky where the waves could have come from. Okay, so here is now finally the real discovery data as seen by Livingston and Hanford. The first event that we saw was only 0.2 of a second long, the entire series of waves. But you can see that the frequency is increasing. So the waves are closer together. You can also see that they're getting bigger. The amplitude is increasing. Here's the final merger event. And then this is called the ring down. It's that sort of quivering, settling down that I showed in the previous videos. And we cheated a little bit because since the interferometers are opposite each other in orientation, you have to flip one of them upside down so you can compare them. Okay, so we cheated just a little tiny bit. So that's the data from the two different LIGO observatories. This event was called GW 150914 because we named them after the dates that we discovered them. And on this slide, this light blue that's drawn on top of here, or the light orange that's drawn on top of here, that's the best fit model from doing the full general relativistic modeling of the wave. And so you have all these models that you can run with all these different masses of objects, all these different spins of objects, and you have to do a matching between your model and the data. And the best match gives you the parameters of the system that you just observed merge. So in this case, wait, let me go back here. I forgot to explain one thing. So on the y-axis is a quantity called strain, and on the x-axis is this time, this 0.2 of a second for the entire event. So strain is what we're directly measuring with the interferometer. And strain is defined as the change in the length of the interferometer divided by its length. So the length for LIGO is 4 kilometers. The maximum strain that we saw in those plots was 10 to the minus 21. That means that each 4 kilometer long beam line is changing by 4 times 10 to the minus 18 meters, or 4 billionth of a meter. That's 4,000 times smaller than a proton. So it's pretty amazing that you can measure the length of this 4 kilometer thing to such precision. It's like being able to measure the width of your hair over something that is a baseline that is the distance to Alpha Centauri, the nearest star, or Proxima Centauri, pick your favorite star. Okay, so it's truly astonishing. And this is the LIGO sensitivity curve. So it shows what the strain is you should be able to detect as a function of frequency. And the sweet spot is here between like 100 and 300 or 400 hertz. Okay, so LIGO was designed to have its best sensitivity 2 orders of magnitude better than what we're detecting in that very narrow range of say 100 to 300 or 400 hertz. All of these spikes are instrumental things, so they're not signals of any sort. They're just noisy things we have to work around. Okay, so why is the LIGO sensitive bandpass, why is that interesting to know what those frequencies are? Well, the basic LIGO frequencies of say 20 hertz to a couple thousand hertz is very similar to the frequencies of sound that your ears hear. Okay, and we'll come back to that point, but let me just show you the parameters that came from the model fit to the curves that I just showed you. The distance was about 410 megaparsecs, or 1.2 million light years. And the masses of these objects were huge. The mass of the bigger one was about 36 times the mass of the sun. The mass of the smaller one was 29 times the mass of the sun. If you add them up, you get what's called the Chirp mass. It was 62 times the mass of the sun. But you might notice the math is a little off, right? There's three solar masses of energy or mass missing. That's the energy that came out in the gravitational wave. So since E equals mc squared, you can convert this mass, 3 solar masses, into energy, and that's a heck of a lot of energy. That's more energy than we see from all the stars that are shining in the sky. It's more energy than the supernovae that we see, you know, all added up. It's an incredible amount of energy, and this is just one event. Yet it's very, very hard to detect because even an event as strong as this one only changes the length of those interferometer arms by this incredibly minuscule amount. Okay, now back to the fact that the frequency range is sort of the same frequency range that we hear. So what we like to do, because this is a gravitational wave, there's no pretty pictures that go with it, like from Hubble Space Telescope or something. We like to do what's called sonification and turn the wave signals into sound so that we can just sort of, I don't know, internalize them better or understand better what the wave is like. And so this one was actually sort of slow and not exactly in LIGO's best bandpass. So I'm going to play this. It's just going to sound, there's going to be a bunch of noise, and then it's going to sound like a thump. And then what we're going to do is we're going to raise the frequency, just shift it up by 400 hertz so we can hear it better. And that will be the second set of noises that you hear. Okay, so if you could hear it on the version where the frequency was raised up, what you heard was what is plotted here, because here's frequency and here's time. Here's the wave signal you saw before. This is called the chirp. So as it gets louder, it also gets to a higher frequency. It's like oop, oop. That's the chirping noise. Okay, you can't hear the chirp that well before we raised it up because our ears aren't sensitive. It just sounded like a thump. When you raise it up, you can actually hear the chirping noise. Oop. I'll play it again. Okay, so now hopefully everybody could hear that chirp. And this was a cartoon that came out right at that time, which I just think is very cute, from the New Yorker. And this is a beautiful poster that's sold by the Contemporary Physics Education Project that explains Newton and Einstein and has these drawings of what's going on done by my wonderful artist at EdEon, Aurora Simonet. And it's got the Hanford signal in orange, the Livingston signal in blue. This is the part where the black holes are still spiraling around each other and the waves are getting given off. It's starting to merge, it's getting bigger, it's getting higher frequency. And then afterwards, you just get the sort of quivering ring down, and that's pretty much the end of it. Okay, so fast forward from 2015 to 2017. At the time that this was made in 2017, these were the events that LIGO saw, and basically that that first observing run. And what this is it's showing the masses of the two things that are merging and making the third thing, and the mass of the third, of the chirp mass of the big black hole afterwards. So here's that first event that I showed you, the 29 and the 36 making the 62. This one was later confirmed, so it's a little smaller. This one was smaller still. Now this black hole that was made here is about the size of Cygnus X1. These black holes were so much bigger than Cygnus X1. Okay, and then these ones are also way bigger than Cygnus X1. Here's another one that's sort of Cygnus X1-like, the final one. But what LIGO found, of course, by discovering these merging black holes is an amazing thing, because it is the first direct evidence for black holes. Cygnus X1 was just inferred by what it was doing to its companion star, but these things exactly fit Einstein's predictions for what black holes should do. It's the first discovery of two black holes in one system, because all the X-ray binaries have a normal star and a black hole, and that's why you get to see the X-rays, because the matter from the normal star gets heated up and turns into X-rays when it's on its way to falling in the black hole. It confirmed the existence of gravitational waves, of course, right? So we have also binary black holes, direct detection of black holes, and really, really big black holes compared to the ones we knew about from X-ray binaries. All of this just by 2017. But we're not done, because that was 4 years ago now. Doesn't seem like that long ago to me, but the next thing that we found was in 2017, and it was the thing that LIGO was designed to look for, merging neutron stars. Now you can see this one is going to be very different. For one thing, it's much longer. For another thing, as you'll see when we get to the end here, something else happens that was seen by Fermi in gamma rays. Okay, so I think you could probably hear the chirp on that one pretty good, and we didn't have to shift the frequency at all, right? So that was really quite a dramatic chirp, and it went on for a long time. This is the gamma ray signal seen by Fermi, and that little ding, the little ring, was 2 seconds later after this merger. We saw a big blast of gamma rays. Actually, not such a big one, but we did see a blast of gamma rays. And so gamma ray bursts and merging neutron stars had long been theorized to be related, but this was the first direct evidence that, in fact, when you merge neutron stars, you can get a gamma ray burst. Now, there's a few caveats here. Gravitational waves are omnidirectional, and they don't get stopped by anything. So whatever direction you're looking at the system from, you can see the gravitational waves. That's not true for the gamma rays. The gamma rays are beamed, so you have to be lucky to be looking where you're seeing the beam. And in this particular case, the modeling has shown that we were not right down the beam axis. We were a little off the side, which is why this is sort of a wimpy burst. But still, this was an incredibly exciting event. Visible light people got into the action after this was reported. There were 70 different ground-based telescopes that were looking to figure out where this was in the sky and to see what exploded. And the winners were a team from UC Santa Cruz with the SWOPE telescope. They saw this object, and then, you know, later it was gone. Okay, so 4 days later, thing had faded. Later, you got to see X-rays. Even later, you got to see radio waves. The paper, the discovery paper that was written about this event, GW 170817, has over 3,000 authors on it. And I am 2 of them. There's so many authors that they couldn't even tell when people got duplicated. But I was on the paper for being part of the LIGO team and for also being part of the Fermi team. So I was actually 2 of the 3,000 authors. But that was about 1/3 of the astronomers in the whole world were authors on this paper. That's how exciting the event was, and how people, you know, how into it people were, that they just took every telescope that they had, ground-based, space-based, and chased this thing down. And then, of course, because NASA telescopes were involved, we get a super cool video. And I would just like to point out there is no sound in space, but that was showing the neutron stars merging. It was showing a big cloud of stuff that the gamma rays had to work their way out of, therefore accounting for the 2-second delay. And then once they got out, then the beam started spreading and it ran into some other stuff and made some more light. And then you get to see that afterglow with all the other wavelengths of light, the visible light, the radio light, etc. And this drawing by my wonderful artist, Aversa Manette, was the Nature cover, the art on the magazine Nature, where we published the discovery paper. And this is called, the reason they call this event the golden binary is because the visible light data proved that what happened was a thing called a kilonova, very wimpy compared to a supernova. But the cool thing about kilonovas is you have all those neutrons around from the neutron star. You get nuclear reactions in all of this heated and injected material that's caused by ripping up the neutron stars. It is those reactions that form at least half of the heavy elements, including gold and silver and platinum and things like that. Supernovae can form, when they explode, they can form the lighter elements all the way up to iron. And so we never had direct proof of where the heavier elements after iron in the periodic table come from. And now we do, because we have proven that they can be created in these merging neutron star binaries. You have that much more energy, you can get to the heavier elements than in a supernova. Okay, and this I think drives it home. These are the original LIGO merging black holes. This is the neutron star in the bottom. This is the one that was 0.2 of a second long. That was the discovery one, right? Here are the other ones. The longest one is like 1.5 seconds. But watch the neutron star binary. This is how long we detected it for. And you'll hear it chirp at the very end. Right? Really quite a different kind of object. It lasts for so much longer. And it's still going, and it's still going. And primarily it lasted so much longer because LIGO's sensitivity curve was tuned to find objects like this. So it stayed in the sweet spot of the detector sensitivity for really a long time, compared to the big, heavy, slower moving black holes that were just a little bit too slow to be in the sweet spot. Getting there. So this is all the in spiral. We got to see hundreds of cycles of in spiral. And there was the merger. So this event stayed in LIGO's bandpass for over 55 seconds, whereas all of these black holes were just a fraction of a second to a second because they were moving so slowly, you could only really see them when they sped up at the very end and merged. Then they got into the bandpass. So at the end of 2018, this is all the stuff that LIGO had discovered. All of the things that are triples are from LIGO. So here's all the black hole mergers that have been discovered. These purple ones are all the X-ray binary black holes, like Cygnus X1. These yellow ones are all the electromagnetically measured neutron stars with masses. They're all about 1.5. And we had the single merging neutron star binary where we got 2 neutron stars that got together and made something that we don't even really know what it is, because it's a little bit too heavy to be a neutron star, and it's too light to be a black hole, because we think that lightest black holes are about 3 solar masses, and this was about 2.4. And so we're not really sure what it made. which means that I have been lying to people for probably at least 20 years, telling them that every time neutron stars merge, you would have a birth of a black hole. And here was our first neutron stars that merged, and we don't know what it made because it doesn't seem to be a black hole. It isn't heavy enough, massive enough. Okay, so now on to the more recent results. So LIGO had its third observing run in 2019, and then we took a break, and then in 2020, and then we shut down with COVID. It was supposed to last for about another month. No more electromagnetic counterparts were found, so no more stars or things that were fading away were found. You can get an app. There's two different apps that people made. One's called Chirp, one's called GW Events, that will notify you when there's an incoming gravitational wave. But in the first part of observing run 3, we saw 33 events. And in the second part, we saw at least 23 events that we've announced so far. I think we may have announced a bit more at this point. And so why are there different observing runs? And why do LIGO is shut down now. Observing run 4 will start in 2022. But just like a particle physics detector, you run it for a while, you figure out where the noise is coming from in your system, you shut it down for a while, you try to fix all those noisy things, you start up again with better sensitivity. And so you can see that when we started observing run 3, the sensitivity had increased quite a bit. And so from seeing one event per month, we started seeing stuff, pretty much every week. I mean, it was just astonishing. We couldn't even really keep up with all of it. And so here's the latest news. There's a wonderful LIGO artist, Destiny, and she has a comic called Antimatter Comics that you might want to check out. This is Ray Weiss, the MIT professor that got the Nobel Prize, one of the 3 people. And I just think this is so cute, right? So here's what LIGO's seen so far. Okay, merging binaries. The first ones are black holes. The second, neutron stars that had electromagnetic counterparts. And now we saw 2. And what's really weird is they were 10 days apart. What appear to be a neutron star and a black hole merging, right? So we had 2 black holes, and we had 2 neutron stars. Now we have one of each. Another thing that people had no evidence of before LIGO and Virgo, that they even existed, because you wouldn't be able to see them unless they were merging. Just like you wouldn't be able to see the merging black holes unless they were merging. So here's an artist's drawing. So you've got this black hole, and and it's sucking matter off the neutron star, which is being tidally disrupted. And so at the end of observing run 3, this is what the masses in the stellar graveyard plot looks like. Every single one of these are merging black holes. All of these triples up here. These purple ones are still the Cygnus X1-like things that are isolated and around a normal stellar companion. We have a second merging neutron star, but unfortunately we couldn't get a good enough position, so nobody could figure out where to point their telescopes. And then that was this one and this one. And then these are the 2 that are the merging neutron, the neutron star merging with the black hole, making a bigger black hole. These are the 2 neutron stars merging and making, we don't know what. Right, these 2 little guys down here. So it's the graveyard is getting quite full now as a result of observing run 3. These are the parameters for these 2 merger events that, as I said, were only 10 days apart in January of 2020. So a couple months before we had to shut down for COVID. The first event was seen by only one of the LIGO detectors, but also seen by Virgo. The second event was seen by both LIGO detectors and Virgo. Here are the distances, about, somewhere between 200 and 400 megaparsecs. So they're pretty much around the same place, same distance as that very first event. But the interesting thing is the masses that you get when you do the model fitting to the waveforms. So the heavier object is clearly a black hole. It's at least 9.7 solar masses, in this case, at least 5.7 solar masses. Oh, sorry, wrong one. The 7.4 and 3.6, I misspoke. This is the Chirp mass, the total mass. And these are clearly neutron stars. The range of mass, 1.7 to 2.2, 1.2 to 2.2, clearly neutron stars, clearly black holes. Pretty amazing. And also not spinning very fast. I didn't mention it before, but the original black hole merger that was discovered was spinning pretty quickly. These guys don't seem to be spinning very much. And of course, I would have to leave you with a simulation of this event. So this is another supercomputer calculation, not an artist drawing like the NASA one. And in there is where the action is with the tidally deformed neutron stars. See, it all got shredded as they merged. So pretty cool. The black hole gets bigger, the neutron star gets ripped apart and swallowed up. I'll show you that one more time. And here's the waves coming out. Here's the in spiral. Now the frequency is getting shorter. Now the amplitude is getting higher as the neutron star gets ripped up. And it's over. Well, what's next? This is the world as seen by gravitational observatories. Here's the two LIGOs. Here's Virgo, it's in Italy, if I didn't mention that. Geo 600, and Virgo has a 3-kilometer baseline. Geo 600 has a 600-meter baseline. It's a test bed. We use that to debug a lot of the hardware before it goes into the bigger interferometers. At the end of observing run 3, Kagra joined in. Kagra is an underground detector in Japan, but it hasn't gotten up to enough sensitivity yet to see anything. We hope that when we come back for observing run 4, Kagra will have good enough sensitivity that it will start to see things as well. And then under construction right now in India, although they probably stopped because of the COVID there, is a copy of the LIGOs. So they're basically using the same hardware and sending it all to India, and India is making the beam lines and doing all the infrastructure work, and then the LIGO hardware will be installed there. And we hope that LIGO India will be online in around 2024. So probably observing run 5 or so. But wait, it doesn't stop there. Just like electromagnetic waves, otherwise known as light, has a spectrum that goes from radio waves to gamma rays. Gravitational waves have a spectrum as well, and you need different kinds of detectors to detect the waves with different frequencies or wavelengths. LIGO is at the short end of the spectrum. So LIGO is looking at the equivalent of gamma rays in gravitational wave space. They're the shortest waves. If you get to a little bit slower waves, the concept is to go into space with a telescope that's usually called LISA, for laser interferometer space antenna or space array, where instead of a 4-kilometer baseline beam line, you've got millions of kilometers between satellites that are shooting laser beams at each other and combining them and splitting them up in a triangle. So these would be for bigger, slower things. You can have waves with a frequency of a year for one wave, or decades. The people that are looking for those kind of waves are using ground-based radio telescopes and looking at pulsars in the sky. It's called nanograv, or millisecond pulsar timing. So you've got these neutron stars spinning around. They're almost perfect clocks. You've got them all over the sky, lots of clocks all over the sky, perfectly clicking. The wave comes by, changes space-time so that now some of them are a little closer, a little further away. All of a sudden, the pulses that you're getting with your ground-based radio telescopes are arriving not quite at the right time. And you analyze the whole sky's worth of these things, you might be able to figure out that a wave came through. So that's a really tough task, but the NSF, the National Science Foundation, has funded this, and people are doing that work right now. And then finally, the longest waves are the ones that could have come from the very beginning of the universe and been imprinted on the cosmic microwave background. And so this is an example of the polarization signal that could be imprinted that could be detected by something someday. So that would be the frequency of all the different kinds of gravitational waves and detectors that we hope to see them with. But of course, so far the only ones that have been seen are the faster ones. But this brings us to the era of multi-messenger astronomy. So it used to just be, when I was doing my PhD, multi-wavelength astronomy was exciting. You wouldn't just look at something with X-rays or gamma rays, you'd also get visible light telescopes and radio telescopes and try to put the whole picture together of what was going on by looking at all the different kinds of light from an object. But now we have the electromagnetic waves, which are the light, gravitational waves, cosmic rays, which are particles, and neutrinos, which are particles. And all these different kinds of detectors, you know, in space, on the ground, big dishes, air shower arrays, whatever. Each type of messenger tells us something new about the universe. And when you put them all together, you get an even more complete picture of what is really going on out there. So that's where we are now. We're in the era of multi-messenger astronomy, and it's a really exciting time to be an astronomer. So let's just raise an in-spiral toast to the rise of gravitational wave astronomy or multi-messenger astronomy. This was something invented by some of our Scottish LIGO colleagues. Oops, I didn't click in the right place. Okay, so with that, I will end. That's the in-spiral toast, which you can all try with some of your friends tonight at home. Here's some links if you want to follow up on some of this stuff. The main LIGO website, where all the individual detections are with the different graphs that I've showed you. I've done a couple of online courses that teach you all about this stuff, which you can see at this link. And this is one of my favorite because it shows all the sonification of the different mergers. And with that, I thank you all for your attention, and I will be happy to take questions. And Stephanie will be fielding those, I think.
Thank you. Thank you so much. We do have a few questions in the chat that I'll just go through and read them off. And for anybody else who has some questions, feel free to put those in the chat and I will read them off. So the first one is there any data sharing among ALMA, LIGO, Fermilab, and LHC CERN? If so, in what area of research? Can you tell us any achievement of LIGO India?
Okay, LIGO India is not yet built, so it has no achievements yet. Now, LIGO and Virgo have signed many agreements with other messengers and other telescopes. So LIGO has a partnership with Fermi, the satellite, but not Fermilab, right? Fermilab and CERN are both particle physics detectors, and they're not looking at the sky. They're just colliding particles and beams and looking at what comes out. ALMA, on the other hand, is a very big radio telescope, and it has an agreement with LIGO and Virgo to listen to the triggers and to then go off and look to see if they see anything, if we can tell them where in the sky to look.
Perfect. The next question is, how is the distance to a merging event determined? Gravitational wave Doppler effect?
Okay, no, actually the distance, so this is really interesting. Because general relativity is so exact in its predictions, when you do one of these model calculations, it not only tells you the frequency of the waves, but it tells you the amplitude. And so you get a prediction for how strong the wave can be, and then you see how strong the wave was when you detected it, and that gives you the distance within the model uncertainties. The distance comes right out. You don't have to worry about absorption by dust or any of those kinds of things. So you just get the distance right from comparing the predictions from general relativity to the signal that you saw.
Great. The next question is, are they always binary mergers?
So far, everything that we've seen is a binary merger. And if you remember that little cartoon with Ray Weiss in it, we'd really love to see a supernova. We'd really love to see an individual pulsar just rotating because it's, you know, not a perfect sphere. We haven't seen those yet. But as we get to more and more sensitivity, and if we get really lucky and get a supernova in our own galaxy, then, you know, we should be able to see that pretty easily.
Next question is, why do gravitational waves travel at the speed of light?
In order to answer that, you need to actually study some general relativity. And this course, one of my courses, Teaching Einstein's Universe courses, the 2015 course has about a 40-page exercise that you can work through. And Jacob, you could probably do that. That will lead you to see why, when you get to the wave equation, the speed is the same speed as the speed of light. So yeah, so you have to actually work through the math to be able to do that, to see that actual number come out of the equation.
Right. The next one is, can GWs, I'm assuming meaning gravitational waves, be related to dark energy?
No, unfortunately not. No. Two totally different things, and we don't really have any clue what dark energy is. But what it does appear to be is sort of a negative gravity, like a negative pressure, like is causing the universe to accelerate faster and faster. So it's pushing things apart. The gravitational waves are just something that comes out when things at this point are colliding together. So it's also very different scales, right? This is two stars like things colliding. Dark energy is something that affects the entire universe, and it's everywhere. It's not located in stars.
Okay. Also, somebody wanted to know, how did you get involved in the LIGO project? Any advice for an astrophysics undergrad interested in gravitational waves?
Sure, come to Sonoma State. We're happy to put you to work on the LIGO project. That would be my best advice. But of course, study as much physics and take as much general relativity as you can. Normally, general relativity is not taught until graduate school, however. But you can learn a little bit about it as an undergraduate and keep working on your very complicated math. How I got involved with LIGO is that I have been studying neutron stars and black holes using X-rays and gamma rays for my entire career. This is going back more than 40 years now. So my very first job out of college was working on data from Uhuru, that first X-ray astronomy satellite. And so I got into X-ray astronomy pretty much on the ground floor. Only a few people have been in it longer than me, and they're all much older than me. And we've been having 50-year anniversary celebrations for a lot of those people lately. But I started doing all the education work that I do in the mid-1990s. And so I was doing education and public outreach for various X-ray and gamma ray satellites. And then the LIGO people asked me to be on their program advisory committee and give them advice about what they should be doing with their education program and their outreach program. So I was on that committee for 3 years giving them advice. And as soon as I got off the committee, I joined the collaboration because it was just so exciting. The thought of being able to study black holes and neutron stars in a totally different way was just so exciting that I was just like, it was like the Borg. I got assimilated, just like hanging out with these people for 3 years. It's like, I want to join your club. And so I did as soon as I got off the official committee where I had to be an independent person.
Wow, that's fantastic. Okay, let's see, a couple more questions. One person wanted to know, can you say more about how such small displacements, a thousandth the diameter of a proton, can be measured?
It's definitely a hard thing to understand. So basically, the way you can do it is because the beam on the mirror covers a very, the mirror's like, this big, and the beam spot size is like that big. And so what you're doing is you're actually averaging over lots and lots and lots of atoms. Wow. So you don't have to worry about measuring just the individual thing compared to like one proton. You're basically doing this ensemble average over the whole beam spot on the mirror.
Okay, good question. This one I can answer. Can this meeting be available on YouTube? We do record all of them, and they will actually be available on our website. They're not up on there yet, but should be soon, all our past speaker series presentations. I also have another question. Is the effective arm length of LIGO 1600 kilometers? Well,
it sort of depends on how you think about it. do the strain calculation based on the actual real length. The bouncing doesn't change the length of it. What it does is it serves to build the power up of the signal in the arm, and you need that power to be able to have the sensitivity to make the detection.
Okay. Let's see. And then one more question. What is the actual nature of a gravitational wave, like the dual nature, particle and wave of election?
He meant electron, but okay, so LIGO detects gravitational waves. Waves are classical phenomenon. The quantum counterpart of that would be a graviton, but LIGO can't say anything about gravitons. Okay, so if you have a theory of quantum gravity and you have the gravitons are the particle version of the waves, like photons are the particle version of the light waves, right? Then you have gravitons in the quantum theory, but LIGO is a classical instrument. It's just like when you use a radio telescope, you're looking at radio waves. And when you use a gamma ray telescope, you're looking at individual gamma rays acting like particles. So it's another one of these things where the thing shows its nature based on the kind of detector that you use. If you're looking for the wave-like nature, you use a certain kind of detector. If you're looking for the particle-like quantum nature, you use a different kind of telescope, but nobody knows how to see gravitons yet, for sure.
Okay. Let's see, we also, by the way, Dr. Cominsky, there's a lot of comments. Thank you very much. Very informational. They love the talk. So I'm not reading through all of those, but there are several of those as well. One more question just popped in. What or who inspired you to study space?
Well, that's an easy one. It was my mom, because my mom was my Girl Scout leader when I was growing up, and she took us camping and taught us the constellations and took us out stargazing. So that was really my first introduction to the sky. And the funny thing is, those are still the only constellations that I know, because as a professional astronomer studying X-rays from space, I don't look at the visible light sky very often unless I go to a place like RFO. So that's so that's probably a good place to end.
That is fun. And we get a lot of Girl Scouts up at RFO. So it's nice to, you know, have that inspiration. I think anybody else there, those are all the questions that have been posted. Anybody want to jump in? You can also unmute yourself if you'd like, or put something in the chat. But if not, I know we went a little over your time, and I appreciate you answering all these questions.
Well, they were very good questions, so it was my pleasure.
Yeah, I think that was all of them. Thank you so much. We really appreciate your time, and it was fascinating.
Thank you very much, everybody.
All right.
Yeah, thanks. Fantastic talk.
Now.
Thank you.
Thanks, Dave.
Great talk. Thank you.
Hey,
Thank you.
Bye, Sabrina. Glad you were here.
Another shameless plug for the Robert Ferguson Observatory is that on September 9th, we are privileged to have Dr. Alex Filipenko talking about new surprises in our accelerating universe. And it's part of the observatory's annual fund launch, so we can raise a little money to continue educating the public about astronomy. So should be a great event, and I encourage you to sign up for that one as well.
All righty.
Thank you very much, everybody. Have a good rest of your weekend.
Bye.
Bye-bye.